which is um, something that some of us do in Australia. I'd like to acknowledge traditional owners of the land on which I'm working remotely today, the Bidjigal people of the Darug Nation, and I pay my respect to their elders, past, present, and emerging. And thank you, Ryan, for the invitation to speak. Further disclaimer is that this is very much work in progress. It's not my full-time day job to think about Aristotelian infinities. So therefore, there is some current literature, some amazing literature coming out that I haven't kept up with, and no doubt you guys can help me keep up with it. But I thought I'd kick off the discussion. Also, I hate repeating myself. So yeah, this is very much work in progress. So overarching research questions. So I guess first I want to motivate an Aristotelian philosophy of maths by talking about why we need the notion of potential infinity, which is one of Aristotle's greatest contributions to metaphysics and philosophy of maths. Then I want to talk about potentialism and actualism in a slightly more modern context, with reference to the so-called domain principle, which we find in Cantor, and also in Zermelo. But then I'm going to harp upon the importance of Aristotelian classical logic and the law of the excluded middle, which is something that both Aristotle and Zermelo agree on. And this is going to bring us back to a bit of thinking about Aristotle's physics and his conception of potentiality. And that's where I might be wanting some more help from Aristotelian scholars, actually in the whole talk. But let's start. So first of all, consider a Kantian antinomy of pure reason. We have a thesis: the world, the universe, is spatially finite. We have an antithesis: the world, the universe, is spatially, So first of all, the world, the universe, is spatially finite. Antithesis: the world, the universe, is spatially infinite. And now the question is, this dialectic, what should be the synthesis? You know, what is the view that kind of transcends both of these limited, incorrect views? The thesis is in some sense Aristotle's view that we live in a finite cosmos. The antithesis is the early modern or modern view that the universe is infinite. But the synthesis has kind of take us beyond that to the idea that the universe is potentially infinite. And this is what we find in modern physics, that the universe is actually expanding. It's indefinitely extensible, if you like, in space-time, because we no longer talk about just space or time, we talk about space-time. So this is the synthesis view we get. And of course, we've left Aristotle behind because we say that since the Big Bang 14 billion years ago, the universe is expanding. At an accelerating rate, no less. So that's one cosmological antinomy, or clashing law of reason. So a second one, and I'm just racing through these to motivate why the idea of potential infinity is still relevant. The second one is another Kantian antinomy, which you can find in the Critique of Pure Reason. The thesis: spatial magnitude is only finitely divisible. It has minimal parts or atoms. That's what the ancient atomists believed. That's what contemporary particle physicists believe. The antithesis is that spatial magnitude is infinitely divisible, that there's no end to the divisions we can make. And then the question is, what is the synthesis view? Possible synthesis view is that physical space-time might be grainy and have clumpy bits, but we've got this mathematical idea of a continuum, and it's an idealization. Whereas in fact, the physical world, there might be limits to what we can measure in quantum mechanics, set by the Planck length. So we get this weird kind of synthesis view. Okay, so a final antinomy, if you're not yet convinced of the utility of the notion of potential infinity, I call this one the modern mathematical antinomy. The thesis would be something like, because this is not in Kant, obviously, the set theoretic universe is itself at most transfinite K infinite, where K is some number. The antithesis would be that the set theoretic universe is beyond K infinite. It's much bigger than you think. But if we, we're led to this view because anytime we suppose that we've gotten to the end of the set theoretic universe, there's always a way of jumping up to a next level and finding something bigger. And I'm probably not going to discuss in detail, but in each case, the view that the set theoretic universe is finite leads to a contradiction. And you can do that either using the Burali-Forti paradox, or you can do it using Cantor's theorem. But in either case, you reach the conclusion that however large you think the set theoretic universe is, no, it's actually larger. So what is the synthesis view? The synthesis view is, which I think maybe Øystein might talk more about, and Leon Horston, that the set theoretic universe is potentially, but not actually absolutely infinite. So that somehow we've got this view of a set theoretic universe, but we can't really treat it as an object in our set theory. And this is the view that we get in a very famous paper of Ernst Zermelo's in 1939, Über Grenzahlen. And it's also the view that we get in the von Neumann cumulative hierarchy of sets. So the basic idea, and I shouldn't talk about this too long, fascinating as it is, because it's maybe not the main point of my paper, is that we start with some element or empty set, depending on what you like. And we can move to the next level of this set theoretic hierarchy by means of an operation. So typically the easiest way to think of it is that we take the power set operation, we gather up the subsets, and this helps us advance to the next level of the set theoretic hierarchy. And we can keep doing this and think of these stages, I guess, of the set theoretic universe as being actual or realized. And it's very consistent, like there's no problem in doing this, but we better not talk about the whole set theoretic universe. So I think that Zermelo really thought that he was preventing set theoretic antinomies. And so he has quite a lot to say about why V, this V, which is supposed to be, I guess, all of the smaller V's, he has quite a lot to say about what stops it from being a set. And Cantor, of course, already agreed it wasn't a set, it was an inconsistent multiplicity, it was absolutely infinite, but it's been really hard to specify why, what is it that stops us? And Zermelo comes up with his axiom of separation, which is just something that stops us from forming sets that are too big, because it says that we carve sets out from existing sets. So we take subsets of existing sets, but that just kind of postpones the problem, I guess. But the main point conceptually is that we do not think of V, which is the symbol we use for the set theoretic universe, as a set. At each stage of the set theoretic hierarchy, we cannot really say that V exists as a whole. And we think of successive V stages as being generated or growing in time, if you like. That's the cumulative, iterative set theoretical hierarchy. So one way to look at this, if you're doing metaphysics, is that V is a potential infinite without being an actual infinite. And so in a way, this Zermelian view is kind of Aristotelian because we have a potential infinity. And so what we want to explore in Aristotelian philosophy of maths is this notion of potentiality. Because the notion of potentiality, I've tried to motivate the conclusion that we need this notion of potential infinity. We're not quite sure what it amounts to, but it looks like we need it to avoid antinomies and paradoxes. And the same was true back in Aristotle's day. I mean, obviously he wasn't dealing with set theory or that sort of mathematics. It was more Euclidean geometry, what would become known as Euclidean geometry. But he still has to deal with paradoxes, mainly Zeno's paradoxes. So the question is, what is this potential infinity? Another question is, where do Aristotelians fit into philosophy of maths, given the mathematical developments that we've had since Aristotle? You might think they have to be intuitionists, but how can they advocate classical logic, as good Aristotelians should, and be intuitionists? They can't, because intuitionists like Brouwer reject the law of the excluded middle. And I did manage to see there's some interesting work by Øystein Lenibo and Stuart Shapiro showing that you can use a possible world semantics to make claims, to make sense of claims about potential infinities while maintaining a steadfast adherence to the law of the excluded middle. So that's been a really nice development. I guess it's coming out of Harvard and some work by Charles Parsons much earlier in some ways. I wanted people to help me think about this, though, because I think Aristotle's own concept of potentiality is very different from what we get on, say, a many possible worlds view in modal semantics for modal logic. So Aristotle's view of potentiality, and I'm not an expert on it, seems to be that it's connected with matter, power, change, and events in the actual world. We never get Aristotle talking about other possible worlds, not in those terms. And in particular, he holds that there are irreducible potentialities. And we've got some issues about making sense of this claim, but there's clearly some way in which it makes sense to say that there are irreducible potentialities. So one example would be my potential to learn set theory may not be fully realized in my lifetime. Okay, so there's a question about the meaning of potentiality for Aristotle and for Aristotelians. And could we do something that was more authentically Aristotelian than using the many possible worlds view? So that's one question. And one speculation about that is that you could use temporal modal logic rather than the many possible worlds view. And I think there's been some work by that on Hintica, by Hintica. And but then a lot of philosophers of maths don't like temporal modal logic. And one of the difficulties with it is it looks like we're going to have to start analyzing statements of mathematics as referring to space and time and the mind. And that's what we get with intuitionism. So maybe we don't want to go there. How am I doing for time? Okay. Okay, well, let's think a bit more about the domain principle. So Cantor's domain principle says that every potential infinite presupposes an actual infinite. And that's just kind of restating the problem, but he more or less converted everyone into accepting this principle with his set theory, thereby, undoing 1800 years of mathematics. So it was really revolutionary. But because of the set theoretic antinomies, we do want to make sense of this notion of irreducible potential infinity. And we also want an argument for the domain principle that is kind of acceptable to a lot of mathematicians and logicians. And it shouldn't be a question-begging argument that just restates a commitment to realism, and it shouldn't, presuppose theological views. So can we get an argument for it? This is the argument that we get in Cantor, and it's a bit obscure. He says, there's no doubt we cannot do without variable quantities in the sense of the potential infinite. And from this can be demonstrated the necessity of the actual infinite. In order for there to be a variable quantity in some mathematical study, the domain of its variability must, strictly speaking, be known beforehand and through a definition. However, this domain cannot itself be something variable, since otherwise each fixed support for the study would collapse. Thus, this domain is a definite, actually infinite set of values. Thus, each potential infinite, if rigorously applied mathematically, presupposes an actual infinite. So you might be thinking, my goodness, how are we to interpret this as an argument for the domain principle? And my attempt to construct an argument is that we should think about an example. So if we think about like a geometric series, 1 plus a half plus a quarter plus an eighth, we want to make statements like the limit of a half to the nth power as n approaches infinity is 2, right? Because in modern mathematics, we think that the series has a limit value and it's 2. So Cantor's domain principle says we should think of there being an actually infinite set of rational numbers that is the truth maker for this statement about the limit of the geometrical series 1 over 2 to the n. Okay, so this set is got members in it like 1, a half, a quarter, an eighth, a 16th, and so on. Of course, I can't fill in the on so on. But Cantor says we have to think of this whole set as existing and being the truth maker of this mathematical statement. And that if we don't do it, then this mathematical statement lacks a truth value, that it is, I mean, he doesn't use those terms, but he thinks that we're not saying anything definite with this assertion that a limit exists if we don't actually believe in the existence of this actually infinite set. But Aristotelians say that you can't think of this set as finished and complete. What you have is a process for generating members of a certain geometric series, but this doesn't mean that the series exists separately from the process of generating it in time. So Aristotelians and intuitionists, they're not going to think of this as a finished set. Zermelians, to add a complication, they would allow that this is a finished set. It's just that there are other things, other classes that are not finished. Okay, so comment on this argument is that Cantor's argument is really obscure. We actually interpret it with reference to Dummett. He's got an old paper on intuitionist logic, and also Graham Priest has commented on it, and they both think that the best way to make sense of it is that the domain principle saying that when we quantify over a domain, we can't get a determinate truth value for that universally quantified claim over an infinite domain, if we don't suppose that that domain is like a fixed actual infinite. So the idea seems to be that if the domain is waxing or waning and it's like it's growing, it's a sequence that's growing, but it doesn't have a fixed identity like an extensionally defined set, then we don't know how to evaluate the truth claims of universally quantified claims about infinite domains. And then one way that people relate to this is by saying, well, you know, statements can be vague. So one reason that we can fail to have a truth value is because the concept we're using is vague. Like, for example, the concept of being a child versus an adult is vague. So if I say that Sarah is a child, this might lack a truth value, except for in law, because it's actually vague when someone turns from being a child into an adult. There's no one moment in time where we say, aha, this person has become an adult. So we just conventionally define a cutoff 18 years old or whatever it is. But then this means that with this vague concept, it's indeterminate what belongs in that set. So there'll be individuals where we can't say, individuals like Sarah, whether they're in that set or not. And instances of the law of the excluded middle are going to fail. But now we have the problem that the law of the excluded middle is a bedrock law of logic for Aristotle. And we want to uphold it. And indeed, Zermelo's very strong realist who says that mathematics without the law of the excluded middle would no longer be mathematics. And I think you can see that because when we prove things by contradiction and so on, we presuppose that the law of the excluded middle holds. So we would like to hang on to this view, but it's not clear how, especially when we get, as it turns out, Gödel shows there are effectively undecidable statements, and these can cause the law of the excluded middle to fail. Okay, so backing up, the main philosophical issue that I'm trying to address is the domain principle. If we put it in modern logic, we're saying, and I haven't said which logic, so you know you can think about which logic, but that if X is potentially infinite, it must be actually infinite. For Cantor, X was a set. And so the question is, how far does that principle hold? What restrictions are there on it? I'm suggesting that a neo-Aristotelian Zermelian view accepts that the domain principle would hold for V, the set theoretic universe. Would not hold for the set theoretic universe, but it would hold for some smaller portion of the set theoretic universe. But you could be stricter than that. But what did Aristotle actually think? I think he rejects the domain principle. He doesn't use that term, but he rejects the idea that all potential infinities are actual infinities. And for him, obviously he doesn't use modern logic, but for him, he's considering moments of time or points on a line or numbers, and he thinks that in most of those cases, the domain principle fails. Yeah, and so then the question is how to actually interpret that in Aristotle. And I won't probably cover all of it, but I think what I want to do is convince you that Aristotle's views are different than contemporary views, which might be obvious. They're really different, and his conception of potentiality is quite different as well. So I will very briefly do that. So what is it to be infinite? Well, Aristotle tells us, first of all, that the infinite, whatever it is, ton aperon, first appears in the continuous. So he's thinking about things like motion. And he's concerned to refute the Eleatics like Zeno, who think that, and Parmenides, who think that change and motion are an illusion and not real. Now, Aristotle acknowledges that there are arguments for believing in the infinite because they do not give out in thought, number, and mathematical magnitude. But he thinks that just because you can think of them in thought doesn't mean that they're real. So he's kind of gives an anti-idealist argument there. It's quite interesting to look at who his actual philosophical opponents are. I think he's opposed to the idea that there are minimal atoms that you could divide magnitude into, which is a view held by Democritus, who he only refers to once. And he's also opposed to the idea that there could be a perceptible infinite body, a soma aperon. So these are his views that he rejects. He's got a very strange cosmos, and it's finite, as I mentioned. And his argument for it being finite is that all bodies have a natural place, and that if the universe were infinite, there would be no place for it to be. We definitely don't accept that framework nowadays. But it was a genuine puzzle. That's what Aristotle thinks. Now we think the universe is actually infinite, and we've discarded this notion of natural place. And also the idea of a center to the universe. We don't hold that anymore either. But what does he actually mean by potentiality? He says being is said, on the one hand, potentially dunamai, and on the other hand, in actuality, entelechei. And the Aristotelian examples we get mainly in the metaphysics are that a builder actualizes his potential for building when engaged in the activity of building, or a learner actualizes her potential for knowing geometry when she's doing geometry, or that a bronze matter takes on the form of, say, a horse statue or something. But none of these examples are actually helpful for understanding what's going on in the physics. Aristotle tells us that the infinite exists dunamai, as a potentiality in thought, but not as something separate in physical reality, which sounds like he's saying it doesn't exist in actuality. So in other words, it's a failure of a domain principle in metaphysics. I think he probably thinks contradiction results from taking the infinite as a separate, actually existing thing. And it's probably because of Zeno's paradoxes. There's some good work on this. So he seems to think that existing in thought is okay for something infinite. We can think about the possibility of taking ever more operations. That's okay. But we don't want to say there's an infinite body. But it's problematic because maybe there's an infinite mind, and so why can't we have an actual infinity? Okay, so Aristotle holds in Physics 3 that all infinity of magnitude is potential, not actual. And he says, I mean, obviously we can keep dividing magnitude. We don't reach these little spatial atoms. The atomists are wrong about that. But so it's potentially infinite, but the question is, why doesn't it trigger a domain principle? And all he really tells us is that, look, don't take potentiality in the same way that where it's possible for bronze to become a statue, it will actually be a statue. We take being in many senses, just as a day is and a contest is. By the constant occurring of one thing after another, so too with the infinite. In general, the infinite is in virtue of one thing's constantly being taken after another. Each taken thing is finite, but it is always followed by another. So he definitely thinks the domain principle fails for the infinite in the case of like spatial magnitude. And therefore, potentiality has to be treated separately from the way he treats it in the metaphysics. And it's still hard to understand why. We think he's probably motivated to avoid Zeno's paradoxes of motion, but we're still after a really good argument for why he won't allow actual infinities. And so maybe the history of maths suggests that he was wrong about that. But he might not be wrong about it when it comes to, say, these issues raised by what we call absolute infinites, such as you saw with the set theoretic universe. And so wrapping up, infinite is always incomplete for Aristotle. It's not the whole, he says. It's a different kettle of fish from the universe or the whole. And then in a very telling statement, he says, the infinite is the material of the completeness of magnitude, and that which is potentially but not actually whole. So I think for Aristotle, the infinite is very associated with matter. It's unknowable, it's potential, it's incomplete. This is the kind of Aristotelian view that we get where everything on the left-hand side is associated and everything on the right-hand side is opposed. That's just based on Physics Book 3. I think I won't have time to discuss bisection of a line segment, but it was implicit in my discussion of the example with Cantor's domain principle. And Aristotle basically agrees there's no limit to the process of making divisions or cuts, but he thinks we shouldn't think of them as all actually existing in reality at once. Why? Because then we're going to have Zeno's paradoxes. We're not going to understand how we can get from A to B. You know, it might have been plausible in Aristotle's day that you didn't need infinite magnitude in order to do maths. You just need to extend a line as far as you please to do Euclidean geometry. And so we are left with these opposing views. And Dummett says that they're like different metaphors. The mathematician as an astronomer, according to the realist, or the mathematician as an artificer, according to the intuitionist. And I think it is useful to think of the Aristotelian, at least from Aristotle's physics, as being focused on the human mathematician in time, constructing lines with compass and straight edge, but in an idealized way. And to think of the Cantorian as focused on some abstract mathematical continuum that exists independently of spatial-temporal intuition. I still don't know how we decide between these frameworks. And so one suggestion that could be made is that we don't have to decide between them. It just actually depends what our purpose is. And so if we want to talk about what geometers actually do, we go with the Aristotelian framework. But if we want to do higher set theory, then we go with the Cantorian framework. So there may be room for both views. And I think I am going to leave it there. Just wrapping up, Aristotle rejects the domain principle in many cases. And it's not clear that his notion of potentiality is the same as the modern logical notion of possibility. It seems to be connected with matter and a lack of form. So it's a natural science notion. It's not a purely logical notion. I think this is as far as I've gotten in my hobby of understanding the lay of the land for Aristotelian philosophy of maths. Thanks.
All right, many thanks to you, Anne, for that very stimulating start to our day. So we have about 7-8 minutes for questions. Please just use the raise hand feature in Zoom. That'll be the easiest way to keep track of who's up. All right, go ahead, Oystein.
Yeah, thank you, Anne. So you'll see when I speak next that we agree about many things here. But I wanted to comment just a little bit on Aristotle on modality and what's needed there. So you mentioned my work with Shapiro and talked about possible world semantics in that context. And yes, we do use that, but very carefully, just in a heuristic role. So the modality has to be primitive, and you can't reduce the modality to quantification over possible worlds, since then you just end up with an actual infinity of worlds instead, and that would be no progress. I'm with you on that. And by having a primitive modality, whatever exactly that is, you also have what it takes to go against the unrestricted domain principle. And this idea that to be mathematically rigorous, you need to have an underlying actual domain. That's simply not so when you have modality on board, and the modality can be made rigorous using modal logic.
Okay, so that's a really, really good point, that we seem to have to accept an actual infinite if we start thinking in terms of infinitely many possible worlds, which is why I said an Aristotelian shouldn't do that. That you're saying that you need to think of the possible worlds in a heuristic role, I think you said, and that modality was primitive. I don't know, can you say a tiny bit more about that?
Well, time is limited, so I'm going to be very, very brief, but we need a primitive modality. I think we're all agreed on that. And then the question is, what is the modal logic for that modality? And when it comes to motivating one modal logic over another, it's super useful just to have the heuristic of possible worlds. And you use that heuristic, that kind of image.
Okay, so
what modality is to motivate agree. One modal logic. Oh.
Okay, so that helps me understand what you're up to, that we're not like reifying the possible worlds a la David Lewis or something, because he has to be committed to an actual infinity of possible worlds. Okay.
Precisely, agreed.
Yeah, okay. Thank you.
All right, Peter. You're still muted, Peter.
I'm sorry. Thank you very much for this presentation. I'm coming from the Aristotelian side and find all this modern stuff very fascinating, how it deals with potential infinite, especially this domain principle. You said that Aristotle rejects the domain principle, at least in many cases. Well, I think it's a bit more complicated because it depends on the criterion for actuality which is involved. And I would suggest that Aristotle has not such a strong criterion for actuality, or liberal, you might also call it, as is presupposed in the modern discussion, because it seems that he counts as actual which is that which is in the present moment existing as in some way, and so he doesn't have any problems with there being what we might call actually infinite many possible worlds or possibilities, as long as they do not are not realized in one single moment. And that's a far stricter criterion for actuality. It's a presentist conception. And so I would suggest that Aristotle can perfectly allow for there being, in our language, an actual infinity of all the natural numbers, for example, as long as he doesn't allow that that there's a number of numbers, but he could allow therefore there being just a plurality of an actual infinite plurality of all the natural numbers, as long as there are no infinitely many natural numbers considered by the mathematician in together or such things. But he can perfectly quantify over all potentially existing numbers and treat this as an actual infinity. So
Peter, sorry,
yeah.
can we just let Anne respond because we're a little low on time?
Okay,
Okay.
so I think I will take that as a comment, and I think I disagree with you. But it obviously takes a lot more scholarship to argue that out, specifically with regard to what Aristotle thinks. You know, like the contemporary philosophy of maths doesn't necessarily care about fidelity to Aristotle's own views, but we have other reasons for caring about it. So I'm not sure at all that I agree with that. But I'll take it as a comment, because we're not going to settle the issue right now because it takes a lot more work.
Okay. Yeah.
And it's even actually hard for me. It's even actually hard. It's hard for me to say why I disagree about that view of Aristotle, because it just takes a lot more work. But I do understand that it's not cut and dried, and there is room for a lot of debate here about what is the proper Aristotelian view.
All right, we started just a minute late, so I'm going to let us sneak in one last question by Martina, but if you can try to keep it quick.
Okay, thank you very much for the lecture. I would also like to comment on the Aristotelian side of the discussion, and I would like to raise a problem regarding Aristotle's answer to Zeno's paradoxes, because from what I've read about the answer by Aristotle to Zeno in Physics 6 and 8, I don't really think that he identifies a contradiction in an actual infinity. I think that his problem is that if you allow the infinity, for example, of half lines to be actual, then you can't cross the line, and you only are able to cross it when it is potential. But I don't think that he's saying that the notion of an actual infinity of half lines is contradictory in itself. And I don't have the time to argue for it here.
Yeah, no, I
but-
agree with that. That sounds really plausible to me, that it's not an outright contradiction, but he is motivated to distinguish maybe between potential infinity and actual infinity, in part because it does help him avoid Zeno's paradoxes. It's not an outright contradiction, but he wants to accept the reality of change and motion. It's a real problem if you can't get from A to B because of, the dichotomy paradox or something. So somehow, if these divisions between A and B, that interval, are only potential, then he thinks that's not an obstacle to getting from A to B. But there's no need to call it a contradiction. So I would agree with that. Yeah.
All right, let's thank you, Anne.
Thank you.